For first order systems, I specifically mean this formula over here is what I take to be the standard form of the first order transfer function, right? And I take to mean the numerator of that transfer function as the gain of the transfer function, and I mean the coefficient of S in the standard form. So take note, this standard form is very special. It's been manipulated in such a way so that the constant of the denominator is 1. And this is known as the time constant form of the differential equation. This is what the standard response looks like, and what I expect you to have committed to memory is the fact that the final value of the step response of that first order system is equal to the numerator of that transfer function in the standard form, also known as the gain. I also expect you to know the properties of this box. So remember, the box goes, the y value, the top of the box is at the gain, at the value of k, and the x value or the time value of the box is at the value of the time constant. If I connect a line from 0, 0 to the top corner of that box, that line will be tangent to the initial response of the system. Also, we commonly talk about that point at which the response crosses through the box. In other words, the value of the response at time equal to the time constant. And I expect you, honestly, you've seen me, I don't actually remember the number. I just remember how to calculate it, 1 minus 1 over e. And it's about 63%. So, but in general, you can kind of estimate that it's about 2/3 of the way to the final response. So those are the properties that I expect you to be familiar with, so that you know that the time constant gives you a sense of time scale, right? And the gain gives you a sense of magnitude of response. Also, at the same time, I'm expecting you to know what the impulse response looks like. And so the impulse response, if you connect a line from the impulse response down to that point, that gives you the tangent of the impulse response. Remember, the impulse response is the derivative of the step response. And so the initial value of this impulse response is equal to the slope at that initial point. The smaller the time constant, the larger the initial slope, and you can see the impulse response climbing up there, that initial value. And so those links I expect you to commit to memory. Now, there's a couple of additional things in the textbook. So I've been speaking here about the impulse response and the impulse response and the step response. But remember that I could also talk about the ramp response or any of the other responses in the table. So basically any of the functions that I have in the table here has a corresponding response. The first couple of them, these ones that go like this, you can kind of see that they are related through integration. So in other words, if I know the impulse response, I can infer or kind of generate from the impulse response, I can generate the step response, the ramp response, and so on, and like the response to a quadratically growing input, which we don't use that often. But I can induce all of those by just integrating subsequent lines. Okay, and that's easy enough. Obviously, from the Laplace type, version of this, every time I put a function like this through that system, I'll effectively get the convolution of those two systems out. So that's the first thing, that's first order systems. What happens if k is 0? Now we are effectively filling a bucket with water. Okay? It's now no longer a tank that eventually will find a level. It will just continue filling up indefinitely. Now, such a system, if you go through the math, you can easily see especially in this form that we derived over here, that if k is 0, this system responds like an integral itself. And so one way of thinking about the level of water in a closed tank or a bucket is that that level is actually integrating the flow rate of the stuff that's coming into it. And we will refer to such a system as an integrating system. And so you'll see the textbook has a couple of examples of integrating systems. The thing that I want you to understand is you can think of an integrating system as a special case of a first order system with a very large time constant. So as you can see, the behavior of an integrating system with k is equal to 0 is very similar to the behavior of a first order system with a very large time constant because that time constant will start dominating the denominator. Right? So we've got k over tau is plus 1. When tau is very large, the 1 is very small in relation to the other term. And so it's a lot like just an integrator system. And so hopefully by now you should have a little bit of intuition saying an integrating system's step response will be a ramp. Does that resonate with everybody? Why am I saying this? Because if we refer to the table, right, an integrating system has a transfer function of 1 over s, or kind of a 1 over s like k over s. A unit step is 1 over s. What's the response of a system with a transfer function 1 over s to an input with a transfer function 1 over s? 1 over s squared. Okay, and so 1 over s squared is the ramp transfer function. And look at what happens when I make the time constant very large. As I increase the time constant, my response more and more resembles a ramp. And so one way of thinking about integrating systems is that they are just very, very slow first order systems with very, very large gains. Does that make sense? Okay, because obviously we're trying to match to get to 1 over s, both the time constant and the gain have to be very large to cancel out to 1. Okay, so there's this kind of mathematical intuition that we can build that relates these systems to one another in quite a pleasing way. Right, so that's first order and integrating systems. First order and integrating systems are the simplest transfer functions that you can think of that show dynamics. The only simpler transfer function doesn't have s's in at all. And remember yesterday, or actually on Tuesday, we mentioned this idea that when you see an s somewhere in the transfer function, that s originated from a derivative, right? So it's because of this. When I wrote down my differential equation, when I Laplace transformed that differential equation, I ended up with a raw s. That's the only place where I see raw s's if I haven't substituted in signals, right? So raw s's in transfer functions only ever come from dynamics. The very simplest version of a transfer function is a constant, no dynamics. The next more complicated transfer function is 1 over s. That's an integrating system with no outflow. The next more complicated system is a first order transfer function. And we've seen that they actually kind of have a very strong family relationship, right? They're actually very much the same kind of thing with one differential equation.